Okay? And so what does this give? So no, time's no longer involved, so what this has to do is the trajectory of the particle, the direction in which the particle is moving. We can pinpoint from this -1/4 centimeters per centimeter. All right, so what about the second derivative? Well, you do the same thing. Given a small change in x, given a small change in x, this is how much the dy dx is changing. So given a small change in x, the value of dy dx will decrease by the same amount or 1 times that given change in x. Right? So whatever the change in x is around t equals 5, the rate is changing, it's decreasing by however much x changes, or a 1 times multiplier. So if we put that all together, we can make a sketch. And really, the only thing we can do with the sketch is in the vicinity of t equals 5. So I said you draw as much as accurately as you are able, but that can only be when t equals 5, and I gave you the coordinates here. So when t equals 5, this is our x coordinates, so we're -2, and at t equals 5, y coordinates 2. So at the instant t equals 5, we're right there. Okay? And so we know it's moving to the right and down. We know it's moving to the right and down simultaneously, and that trajectory was 1/4, right? 1/4, that came from dy dx. So we could give a target kind of like as a target here. So at that moment, so over 4 and down 1, so something like that. And then we can also use the dy dx. So for a change of x of -1, the rate would decrease by 1. That's what that negative the second derivative of -1 meant, right? So if this second derivative remained constant, and we'll just assume it remains constant, that means if we change x by 1 second, change x by 1 horizontal amount, then the rate will what? Decrease by 1. What's the current rate, dy dx? It's -1/4. So for an increase of x of 1, what would the new dy dx be? Right, so here dy dx is equal to -1/4. So then increasing x by 1, right, plus 1, would mean, we don't know where it is exactly in y, but we can just predict maybe something like this. And then now this new dy dx would be approximately -1/4, what? -1. Because for a change of x of 1, the second derivative tells us that that is going to decrease by 1, or -5/4. So somewhere down here, now it's going to be, I don't know where it is in y. I don't know exactly where it is in y, but it's going to be a little bit steeper than 1. So we can kind of put this together here and say that the path is kind of like this. So I'm getting a new dy dx. For a change of x of 1, the old dy dx is going to decrease by 1. That's -5/4, which would mean that at x equals -1, something like a trajectory like that. So this is the best I can do here. And now, just the dy dx and the second derivative don't give us the direction, right? They just give us kind of the orientation of the path. But looking back at dy dx and dx dt and dy dt, we know it's this way. We know it's to the right and down. Okay. Any questions? Yes, please. Can't really, so this is even pushing it here. So, because this is a big change in x. So I did all this stuff about the second derivative with a big change in x, which is kind of, that's making assumptions in itself. So really, all the information we have is only right around t equals 5. You can't really know anything except in this vicinity right here. So even what I did by extending, by making that change to x1, that's a big change in x, but it just made the numbers easy and gave us something to do. But beyond that, you really can't, because everything was about t equals 5. Yeah, so that's what I did as well. So you just kept going down like this, kind of? Yeah, that's okay. But the point is that as soon as you move away from that point and some time goes by, everything's off the table. It could all change. Even the second derivative could change. Other questions? Okay, hopefully that was helpful, and then this going over it was helpful. But super important, right? So derivatives are about rate of change, and so we want to always keep those meanings in mind, all right? And know them well. We need to know those meanings well. So I will post, I'll go ahead and post the solution on Blackboard, okay? All right, so then you've got web work due Wednesday. We'll finish up what you need for the web work today. And then you have a project due the last day of class. Let's take a look at that. All right, the project is about Clara, the calculus cow. And she's been tied to a silo. And the radius of the silo is 2 meters. And the rope is attached at the westernmost spot on the silo. Right here. That's where it's attached. And the rope is just long enough for her, if she wanted to, she could reach the easternmost point. But just barely long enough to do that. Okay, and so this project will take you through lots of questions about, let's show the much nicer version of this. So I just want to show you. So it's a 2-page project that will give you all kinds of experience or practice with all these concepts we're learning about parametric functions. So the idea is, what is the path? First of all, what is the path that she could walk if she kept the rope tight? If she kept the rope tight, what is the path that she can walk? So this would not at all be convenient as y as a function of x. Okay? Not at all convenient, y as a function of x, because it's not y as a function of x. You'd have to piece together several different things, and it would be really ugly. But as a parametric function, it's very doable and much more convenient. Okay, it's much more convenient and appropriate to use a parametric function. And so, but it's not a function of time, but rather a function of angle measure. So let me show you how this works here. So pause it right there. So there's always a point where the rope is peeling off. Okay? There's always a point where the rope just starts to peel off. Maybe that's right there. And if you extend from the center of the silo to that point where it's peeling off, what we have is the standard trig angle, right? Swept counterclockwise from the 3 o'clock position or on the circle or the positive x-axis. That's the parameter. Okay, the parameter is not time, but it's the parameter of the angle between the positive x-axis swept to the point where the rope is peeling off. So this angle right there is what we've been dealing with so far as t, right? But it's going to be an angle now instead of just t or like time in your homework. Okay, so this is the parameter. And remember, with parametric functions, the parameter is a variable. It's the independent variable, right? So the question is, the first thing you're going to do, which is a huge part of this, is what's the position of Clara, x, y coordinates, parametrically as a function of that angle theta. Okay? So what is the x-coordinate of Clara and what's the y-coordinate of Clara? In terms of that angle, which is not, okay, and be sure you know, it's not the angle from the center to Clara. It's not this angle. It's the angle to the point where the rope is peeling off. So that's our parameter, that's our input, our independent variable, and then our parametric function gives us the position of Clara as she's keeping the rope as tight as she can. Okay, as she's keeping the rope as tight as she can and walks around. Once you get those parametric equations, then there's all kinds of questions using those. How much area does she have to graze in? So what's all the possible area she could graze in around the sideline? What's the furthest she can get to the east? Okay, questions like that. All right. And the worksheet kind of walks you through in a nice succession, the appropriate succession of questions. And so here I want to strongly encourage you, don't go on to the next question until you are 100% sure you've answered the previous question correctly and understood it correctly. Because you'll start, if you don't quite get it or didn't get it right, and then when you go on to the next question, well, then it's just going to go downhill from there. Always make sure you're 100% confident about what you've done so far before moving on. Okay, so any question? This is being recorded, so it's on the video. But any questions that you can think of right now? Yes, sir. Yeah. Yeah, you can come get help from us. Yeah, you absolutely can come get help from us. And so just expect our help to be, asking questions back to you and helping you figure it out for yourself. But we will definitely aid you. But we won't sit there and do it for you. Okay? We're not gonna just say, oh, you have this wrong, and here's what it is. We'll guide you along. Okay? So that's you're in the end are the ones figuring it out. But we'll definitely help you if you need help. Okay? Other questions? Start early. Don't wait till Wednesday or Thursday next week. There's a significant amount of work to do that will take some time and thinking. It's going to take several sittings, multiple times working on this to get it. What it's going to be worth, it's going to be worth normally it's the amount of 2 written homework assignments, plus there's an extra credit component to it, okay? The extra credit component to it is I'll explain it more, but it's kind of like if you do some extra exploration on your own and give a really professional submission. That's where your extra credit can come in. So if you go above and beyond what the questions are asking and show that you're digging more deeply, and then you turn in something that's really professionally put together, then you're qualifying yourself for some extra credit. Okay? Any other questions on the project? Get started early. So this is something you'll be thinking about. Yeah. Yes. Good question. Yeah. Great question. Other questions? Yeah. Yeah. So my animation has her so it's like there's a fence there, right? So my animation would be if there was a fence here. If there were no fence, then yes, she could go all the way down around underneath. Another question back there? Okay. Are we good? So as you start working on it, I hope certainly before this Friday, you should start working on it, and I can put the animation back up, and you can look at it some more, and then have possibly more questions. Okay, cool. It's a good project. It's just the right amount of difficulty that you have to think. It's challenging. You have to think and work at it, but it's attainable. Many students in this class and past semesters have had great success on this, okay? So it's just the right difficulty. Okay, so let's go back to this one. Okay, so here's this next question on your homework was, when the particle is furthest to the right in the plane, what, if anything, can you say about these three derivatives? So that's what I want to know about the anteater here. Where's the point on this curve that's furthest to the right? Where's the point on this curve that's furthest to the right? How am I going to figure that out? Or in other words, where is the x value the greatest? Where's Derek Tran? Is there? Oh, yeah, did you think about that for the homework? So I want the point that's furthest right on the curve. Can you see it?
You want the highest value of x.
Okay.
So you would use the dx dt equation.
Okay, and why does that work? Okay, so he said you want the highest value of x, so use the dx dt. So going back to our meaning for dx dt, why does that make sense that we should do that?
Because for any small amount of t,
Right?
value of x will be like multiplied by, any small value of t would be multiplied by a certain ratio to get x.
Okay. And so what do we want that change in x to be? At the furthest most right point for a change in t. Yeah, this is the key to it. So when t changes a little bit at that furthest right point, how much should x change at that moment? 0. Not at all, right? Because this should be going what direction? Vertical change only, right? No horizontal change. And that will give us what? Furthest to the right and furthest to the left points are when dx dt will be equal to 0. Make sense? That's what dy dt, we don't know. dy at the furthest right point because all of the motion is in the y direction. So for a change in t, you're going to get some either positive or negative value for dy dt. Okay? Vertical change only, so we're going to do that. So we're going to take dx dt, which is super easy derivative, 3t squared minus 6t. And we want that to be 0. How do we handle that? How do we solve? Quadratic, we will factor out 3t, right? B, t minus 2. So therefore, t equals 0 and 2. Give us a dx dt of 0, meaning no horizontal change. And that's going to correspond to places on the curve that are furthest to the right, or have the greatest value of x, and furthest to the left in the local area, right? So like local maximum as far as right and left. Okay? So, well, which one is it? So we need to figure out. So there's actually 2. Do we see anywhere else here that has what's it, vertical? So vertical, so another way you can think of this, vertical tangent, right? Vertical tangent. Kind of looks like there was only 1, but supposedly there's 2. So what can we do? We can just take the t value and, yeah, so if you plug in, say t equals 0, what do you get? X equals, y equals. So that looks like the one we were interested in, right? 1, 4. So that's the furthest. There it is. T equals 0, x equals 1, y equals 4 is the furthest to the right that this curve goes. Now what about the other one? So there was another one that we weren't kind of expecting there. T equals 2. Anybody got this? So I'll just trace on the curve here. Without the software, what could you do? Just plug it in and get those coordinates. But what happens here is the direction of the curve is this way, so this is increasing t. So we're still, 2 still isn't in the picture here. I'll zoom out again. So what happens is what we weren't seeing is that this actually curves back around to the right underneath that we didn't see before, right? Because I wasn't showing that. It's coming out to the left, but then at t equals 2 at the point -3, -18, it actually starts curving back to the right. And so then there's a local, leftmost point, and that's at t equals 2 when x equals 3 and -18. Okay, questions on that? So then I'll leave, so highest points and lowest points on a curve follows pretty easily from that. Use the same logic, your meanings of the derivatives to get highest points on the curve and lowest points. Any questions on that? Okay, again, we're looking for a change in x of 0 when t changes a little bit. That means no horizontal motion, which is going to give us places out at the far right side locally and far left side, like this one, of our curves. Okay, so let's talk about area. Change the subject here. Okay, so let's review. How did we find it? Just in if y was a function of x, how did we find area? Okay, yep, that's right. We did a typical strip. And what was the area of that typical strip? Base times height, which was? So delta A for the strip. Base is delta x. Height was y, or f of x. And so then the area, say from A to B, was the sum, right? German S, sum up all the typical strips, right? The areas of the typical strips is going to be y delta x. Okay, so now if we want to come up with area, get some area calculations, but we have a parametric function. We're actually going to use the exact same thing. This is going to be our starting point. We're not going to start over and redo this. We're going to use this as our starting point, and we're just going to convert this into the variable t. So don't start over. We're going to use that. This is dx, sorry. And then change variable to t. Okay? So if y is f of x, and let's say that x equals, I should use this here. I'll use say capital F, okay? So x is little f, and y is g, say, t. So say the same curve is now x is a function of t and y is a function of t, right? This is our parametric function. Then what? So these are, first of all, these are x values. So we need the corresponding t values. So this same thing is going to be, right, the t that gives me x equals a and the t that gives me x equals b, first of all. I'm just going to change variables, right? So there's a certain t value that's going to give me x equals a and a certain t value that's going to give me x equals b. And then what's y? What is y now? G of t. So my function I'm going to integrate is going to be what y was before, g of t. And then what's dx? So we need to figure out what dx is. So if dx is f of t, then, or sorry, if x is f of t, then dx is, the differential is going to be f prime of t, right? But dt. Remember that with implicit differentiation, right? Implicit differentiation. So if x is f of t, then dx is f prime of t dt. So that's what dx is. And so I've got my formula for area in parametric. But notice, it's the same thing as what we did before. It's just rewritten in terms of t. It's not like we're starting over. So you have to keep the mindset when you're doing these problems, you have to keep the mindset that it's still essentially this. Which means what is true? A is normally how positioned relative to B? When we think about doing these integrals from A to B, we think about what's the orientation of that? Left to right, right? Left to right. It's still the same thing. It's not lower value of t to higher value of t. It's left to right still to get a positive result of the integral. You're still going to think from left to right, okay? And then our g of t is y, and then all this is dx. So we're using this formula, but our mindset, we do these problems, we keep in the mindset of left to right y dx, okay? All right, so let's look at this and let's do an example. So suppose that I'm going to integrate. We good so far? So let's go from when x is -3 there. So that's about t equals -1. Okay, so right here, I've got the point. T equals -1, okay? And x is -3. Looks like y is 6. Okay? And then if I come around here, increase t, follow it around until I get to this root here. Here t is about 1.45. Let's call it 1.45. And y is 0. And x is about -2.26. Okay, so that's that first point there. And there's that point there. So the question is, what if I were to do this integral? I'm going to integrate from -1 to 1.45 of g of t f prime of t dt. So I want to figure out so this is kind of confusing because, or it's not apparent, it's not easily apparent because why? Because the curve comes over here to the right and then wraps back around to the left. And we know this is supposed to give us something to do with areas, right? Something to do with areas, but relative to our old school integral y dx area, right? So what we can do to figure out what this is going to give us is we can break it up. We can take this first part until it starts turning back to the left again. And when is that? Where does it start turning back to the left? That was when t equals 0, right? So we're going to figure out what this gives us, we're going to break it up into two integrals. We're going to go -1 to 0 of y, right? This is y dx, right? G f prime. Okay. This is our f of t up here, right? This is our f of t for x. This is our g of t. Plus, then from 0 to 1.45 of that same thing. And that will be the same as integrating that original integral that I wrote down. Is it fair? So I'm just going to split it up into two parts. So the first one, what is the meaning in terms of area? So why don't you take a minute to talk about that? So based on what we said, all these integrals are based on just y as a function of x area integrals, right? So if you go from -1 to 0, gt f prime of t dt, what's the meaning in terms of area? Or what value will you get in terms of areas in that picture? Why don't you talk and see what you come up with? Go. Okay. Where's Pink Fei? Pink Fei. Liu. Last name Liu. Pink Fei Liu. Here? Not here. Okay. Alexander Castro. Tell me what you talk about. What you think? Okay. Y value. Right? Okay. Right, so this is, right? Okay. So what's the meaning of this value, this whole thing, in terms of areas in this picture? So, okay, so this being the top, from here to here, this curve from there to there, and you're saying all the way down to the x-axis. So if I were to extend this down like this, what's that going to be? Y, x equals -3. So I'm going to make a line x equals -3, and then what's the other one? X equals 1. Okay? And so just looking at, so forgetting about every other part of the curve except from there to there and then down. So it's, what you should have said is it's going to be, I'm going to crosshatch. Vertical lines, okay, thanks. How about green? Does green show up? Okay. All right. So that black thing that I crosshatched is what that first integral will give, that area, right? Starting from the top of it's the curve, just that part of the curve, all the way down to the x-axis. Okay, now, same thing here. What about this? What will that meaning be in terms of area? Yes, sir. Okay, the area beneath the lower part. So will it be the area beneath this down to the axis? Is that what it will be? Agree? What? I thought I heard someone. It's not quite it. What's different about this? What? What's that? No, now I'm talking about the second. I'm just talking about this right here. So now I'm following the curve from here to here. Is it the area underneath that curve to the x-axis? And why or why not? Well, kind of, but not quite. Yeah. See? You got it. What did we say? This is still like our old school integrals, but now this is further to the right than this is. So yeah, t is lower here than this, but this x value is greater than this one, so we're integrating now what? From right to left instead of left to right. So then that will give us what then? The opposite of this. So we're going to get all of this area that I crosshatched with black, plus the opposite of what I crosshatched in red. So that means that the original integral will give us what? So we're going to get all this positive area from the first integral, plus the opposite of what's red because it's going from right to left, right to left. So therefore, this thing will give us what? What will that give us? Talk to the person next to you. Go. So when I take the total area of the black crosshat region and add the opposite of the red region, what do I get? What do I get? Somebody new, volunteer. What do you mean by over the y-axis? This part right here? This part here? This little part right here? Okay, so is it that little part right there? You could raise your hand. Okay, so can you kind of describe what that area is? Yeah, so it ends up kind of being like the area inside of the curve. Do you see that? But then with the boundary of this line and this line. So let's see, I'll do that in blue. I'll make this a real mess. Ready? So this is the area that it's actually going to give us. It's all this area here, like kind of tucked inside of the anteater's head and neck. So the original integral, if I do that integral, it's going to calculate that area right there, because from here to here, it's going to give me all of the black area. From -1, t goes from -1 to 0, it's going to be all this black area here. And then when I go from 0 to 1.45, it's going to be the opposite of the red area, so that's going to get subtracted away, leaving me with a blue. Leaving me with a blue. So if we were to actually do that, so I'm going to have the computer do it, but let's write out what it would be, first of all. So that -1 to 1.45 is, what is g of t? This is how you would do it by hand. -2t to the 4th plus 3t squared minus t plus 4 times f prime dt. We found f prime was what? 3t squared minus 6t. So there's the integral for doing it by hand, right? And that would be it'd be a lot of terms, right? You'd start off with 8 terms, you'd multiply this out, get 8 terms, combine your like terms, and then you'd have an easy polynomial integral, okay? And the number you get when you evaluate that will be the area of the blue region. And so can we quickly figure that out? So this is 5. And this is what? -3 and 1. So maybe that whole black region there is about 5 times 3, about 15 or 16. So this one would be about, the first integral would be about 15 or 16, say 15.5. I'm just making a rectangle out of it. 5 by 4, 20. See what I'm doing? Width is 20, width is 4, height is about 5. I'm just kind of averaging out what the height is. So maybe this first one's about 20. What's the second one? Width of about 3, height of about 4, makes that 12, and that would be negative. So we're expecting this final integral, all this area, to be about how many square units? About 8. Let's put it in and see. Sorry, that's the whole integral, not just the inside. Somewhere I have that in here. -1 to 1. Okay, 10.6. So our estimates were off, but that's the idea. So -1 to 1.45 of dt f prime t dt. I think this first estimate was too small. This 20 was too small. So the blue region, 10.62. Okay, web work due Wednesday.